This lesson's on thermal physics and specific heat capacity and calorimetry. Here are your objectives. We can ask ourselves, why do coastal regions or areas near bodies of water have more temperate climates with less fluctuation in temperature than places like a desert? Well, it comes down to specific heat capacity. Specific heat capacity is defined as the energy required to raise the temperature of a unit mass of a substance by 1 degree Celsius or equivalently by 1 Kelvin. By unit mass, we mean either a kilogram or a gram, depending on the context. And we give specific heat capacity the symbol C. We use it in this formula. Q, as we've seen, is energy or heat. And the energy gained or lost by a substance is equal to its mass, given the symbol M, multiplied by its specific heat capacity, C, multiplied by the change in temperature. And so the specific heat capacity is a measure of how much energy you need to put into something to get it to change temperature. Rearranging this, we can think of it as C is equal to Q over M delta T. For a given mass, if the mass stays the same, if you have a higher value of C, it takes a higher amount of energy, greater Q, to get the same temperature increase. So we can think of specific heat capacity like thermal inertia. Just like the inertia of an object causes it to resist acceleration, resist changes in velocity, the specific heat capacity is a reflection of an object's resistance to changing temperature. Also, remember that temperature is a measure of the average translational kinetic energy of the molecules in a substance. And so if you have a higher specific heat capacity, it means it's harder to get the molecules bumping around faster than it is in another substance. Let's do a problem. The specific heat capacity of liquid water is given here, and this is a high value for specific heat capacity. How much energy is required to raise the temperature of a 10-liter tub of water from 10 degrees Celsius to 40 degrees Celsius? Well, first, just a reminder that the density of water is 1 kilogram per liter, so this is a 10 kilogram mass of water. We use our formula, Q is equal to mc delta T, and we just plug in. So we've got 10 kilograms multiplied by 4,186 joules per kilogram degree Celsius, multiplied by our 30 degrees Celsius temperature change. And our units work out so that we end up with joules. So we have 1,255,800 joules, or if I imagine that all of this was two significant figures, let's say that this is 1.3 megajoules. So I said that this specific heat capacity for water is very, very high, and that's because water has hydrogen bonds, and as you add energy to it, it takes a lot of energy to disrupt those hydrogen bonds and increase the average translational kinetic energy. Not all of the energy that you're putting in is increasing the average translational kinetic energy. Much of it is disrupting those bonds first. And so water has a very high specific heat capacity, and that answers the question that I posed at the beginning. If you live near a body of water, that body of water will take in a lot of energy during warm periods, let's say during the day, and then it'll be slow to cool down during cool periods overnight, and as it does cool down, it will release a lot of energy for every degree Celsius. So it will tend to warm the area around it. Let's talk briefly about another unit of energy that we can use, and that's the calorie. A calorie, spelled with a lowercase c, abbreviated like this, is the amount of energy needed to raise 1 gram of water by 1 degree Celsius. And if we use a capital C, then that's the same as a kilocalorie of the lowercase c variety. So a capital C calorie is the amount of energy needed to raise 1 kilogram of water by 1 degree Celsius. By the way, the calories you see listed on your food are actually kilocalories. They have a capital C. So that's another unit of energy, and we can convert back and forth between calories and joules. A similar word is calorimetry, and that's the study of the heat transferred between objects. The principle underlying calorimetry is that the energy lost by one object must be gained by another. In other words, the energy out of one must be equal to the energy into the other, and that's assuming that there's no loss to the surroundings. Here's a typical example. We're going to take a 100-gram piece of aluminum, which has the specific heat capacity as given, and we're going to put it into a tenth of a liter of water that is at a temperature of 0 degrees Celsius. So here's my aluminum. It starts out at 100 degrees Celsius and the water is at 0 degrees Celsius, and we're asked to find the final temperature. So again, we're told that there is no heat transfer to the surroundings, so all energy that is going to be transferred is going to be here. Specifically, it's going to go from the hotter object, the aluminum, to the water. So the principle here is that the energy out of the aluminum is going to be equal to the energy into the water. And we're going to use our equation Q is equal to mc delta T to work this out. So the mass of the aluminum multiplied by its specific heat capacity multiplied by the change in temperature that it undergoes is equal to the mass of the water multiplied by its specific heat capacity multiplied by its change in temperature. We're going to set this up so the change in temperature on both sides are positive. So subbing in, I get the mass of the aluminum, which is 0.1 kilograms, multiplied by its specific heat capacity. And I'm going to set this up so that it is 100 degrees Celsius minus the final temperature. I'm going to let TF be the final temperature. And so I'm setting it up on the left side so that this expression will be positive. And on the right side, I've got the mass of the water, which is also 0.100 kilograms, multiplied by its much larger specific heat capacity, which we said is 4,186 joules per kilogram degree Celsius. And now I'm going to write this as temperature final minus the initial temperature, which was 0 degrees Celsius. Simplifying, I get 9,000 minus 90 times the final temperature is equal to 418.6 times the final temperature, and solving that, I get that the final temperature is equal to approximately 17.7 degrees Celsius. And I'm just going to imagine that all of these were 3 significant figures and leave it there. So just a couple things to notice. Again, on the left side, I set it up as initial temperature minus final temperature, and on the right, I set it up as final minus initial in order to get positive values on both sides. Also notice that the specific heat capacity of water was much, much larger than the specific heat capacity of the aluminum, so it makes sense that the final temperature was a lot closer to the initial temperature of the water. Even though they started off with the same mass, the water has much more thermal inertia, and so the final temperature is much closer to the initial temperature of the water. So that's an introduction to specific heat capacity and calorimetry.